Today we're going to take a look at writing the equation of a quadratic function in standard form. So what we worked on recently is being given the equation, sketching the graph. Now what we're going to look at is either being given the graph or the characteristics and then being able to write the equation. So we're doing the reverse. But it's using the same exact principles and kind of foundational understanding of what quadratics are, some of the key characteristics like the vertex and additional points, but we just got to work backwards now. So just real quickly here, this is going to kind of help us as we start to write it in vertex form. We have to understand what x squared looks like and then the relationship between x squared and 2x squared. So we've graphed these already this year, and as I go through and create the table, I choose my x values, I get my y values back. When I square these x's, because that's what I do, I plug in the x to square them, I get these values. And when I plot the points, I've got the vertex at 0, 0, 1, 1, 2, 4. But then we always understand that there's this axis of symmetry that cuts through the middle of the parabola that really makes what's happening on one side of the parabola happen on the other side. It's that mirrored image. So same distance apart from the midline are these two coordinates across from each other. So when we plot our points, it looks like this. Now, the reason why we're graphing these right now is we're looking at the relationship between the vertex and the nearest points to the right or to the left of it. And notice what happens. One spot over from the vertex is one spot up. So it has like a one-to-one relationship. For two spots over, it goes 4 spots up. At an x value of 2, it goes 4. So it's got a 1, 1, a 2 over, it goes 4 up. 3 over would be squared, would be 9 up. So the next one would be 3 over and 9 up. The next one would be 4 over and 16 up because it's squaring. Now, look at that compared to 2x squared. When I graph 2x squared, and we plug in the numbers, we square them, but then we have to multiply them by 2. All I'm really doing is taking each of these values in the y column and multiplying them by 2. So my table for this one would be negative 2 to 2, but then take these, square them, and multiply by 2. We get an 8, a 2, a 0, 2, 8. So look at what has happened. 0, 0, 1, comma 2, 2, comma not 4, 2, comma 8. And then mirrored image across because of that axis of symmetry. And now we can see that our graph has been what's called vertically stretched by a factor of 2. It is skinnier because it's vertically been stretched. It has that multiplier of 2. So notice this relationship. Over 1, it's actually up 2. Over 2, it's actually up not 4. It goes 8 up, multiplier by 2. Compared to what it should have been at 4, it's now at 8. And then the next one, 3 over, instead of being 9, since it's a multiplier by 2, it will now go 18 up. So what we're trying to do is look at the relationship between the a value here, finding the multiplier that's in front. Because if we're going to try to write the equation in vertex form, which we're going to do here in just a second, it has a multiplier in front many times, a times x minus h squared plus k. Now we know this value h and this value k, those are from the vertex. But this a value is that stretching or the compressing to either flatten it out or make it skinnier. So what's the relationship between the vertex and other points on x squared? So just to have it kind of cleaner in this line here, from the vertex, one spot over goes one spot up, 1, 1. Vertex, 2 spots over goes 4 spots up. 3 spots over goes 9. 4 goes 16. And hopefully you guys are seeing it's just a squared relationship. 5 goes 25. And that's what's happening with just x squared. So if I know that's my basic x squared, well, 2x squared is 1 spot over, doubles it, okay? Take each of these values right here and double them because it's multiplied by 2. So it goes 2. 2 spots over doesn't go 4, it goes 8. 3 spots over doesn't go 9, it goes 18. 4 spots over doesn't go 16, it goes 32. And 5 spots over doesn't go 25, it goes 50. So it has a multiplier of 2. So what we're going to do on these next couple examples is just write the equation given the vertex that is identified in the graph, and then using this relationship we just determined and figured out of the 1, 1, 2, 4, and understand that and compare it to what our graph is, and then maybe we could find our multiplier, like this number 2 in front. Maybe the multiplier is just a 1, meaning it's like the normal relationship right here, like a 1x squared. Maybe the multiplier is a half. So like instead of 4 over up 16, it actually moves only 8. So it's half of what it should be. So let's go through these examples and see what we can do for writing the equation. So in vertex form, a times x minus h squared plus k. This here, h and k, those are the vertex. Well, the vertex is at -1, -1. So my equation, x, careful here, if it's -1, negative, negative, it's actually +1 squared minus 1. And think back to what we've done with vertex form so far. This is, as we've looked at it in the past, this one is always opposite of what you would naturally think. So that +1 actually means it moved left 1. So that is correct right there. So that's why it's a +1 here. This one always stays the same. So that one's the same in terms of movement, you think down. This one is the opposite in terms of movement, left or right. It's opposite of what you would naturally think. Now here's the final part, a value. That's what we just talked about prior. Look at the vertical stretch or compression. If there is no vertical stretch or compression, it's just a 1 in front of it, and you don't even have to write anything. So we take our vertex and we go one spot over, like one x value, okay, not just a single tick mark. So look at the scale here. Notice how this is -1, so I need to go to 0. So it's actually 2 tick marks. So -1, I go over to 0 and I look, and it only goes from -1 up to 0. So it's only 1 over, it moved 1 up. Well, what does that mean? That means it's our basic one. That's our normal type of x squared function, 1x squared. So if you want to write that 1 there, feel free. You just don't have to, okay? You don't need to put that multiplier by 1 because it doesn't really do anything. But that's the a value for this problem because we saw it had a 1-1 relationship. Let's look at the next one. Number 2. Here's our vertex. So it's +1, +1. So let's create our equation, x minus 1 squared plus 1, and that gives us the vertex of 1, 1, and then a value. Vertex here, remember if I'm at an x value of 1, I need to go to 2, so 1 spot over, and it's at a y value of 1, it only moves 1 down. So 1, 1, so the a value is 1. But here's the issue. Look at the direction it's facing. This is concave down. So the parabola is facing down, which means it is a reflection. And how do you reflect the graph? Negative in front. So you could just put a negative, then the parentheses, or you could put -1 and then the parentheses. Either one is okay. But since it's facing down, it has to have that negative. And then number 3, vertex is at -1, -4. So we're right here. So equation time. -1, so +1, -4. Okay, that's -1, -4 for the vertex. Good. Now I'm at x equals -1, go to 0. So 1 x value overs here. And then you have to identify the coordinates that it's there and see how much it's moved vertically. So the value is right there at -6, but it was at -4. So this question's a little confusing because of the scale. Look at the x values, how they're going by ones, and each tick mark is actually technically a half. The y values are going by twos, and each tick mark is actually technically a 1. So just be careful with that. It looks like it's the same movement over down, but the scale tells us differently. So over 1, it actually moves 2 down. So it's only supposed to move 1 if it's our standard at 1x squared. but it's double that, it's twice that, so it's a 2 in front. Okay? Last thing though, look the direction it's facing. It's concave down. So I need to reflect it by throwing a negative. All right? That's our vertex form, creating the equations and going from there. The additional type of question you could see is they don't give you the whole graph, they just give you maybe a vertex and a point. So let's say example, the vertex is 4 comma 5. So we're here and here. So you could plot it, and they give us the coordinate 5 comma 6. 5 comma 6. Well, in order to write the equation and the exact equation, we technically need 3 points for a unique, meaning it's the only one that fits it, a unique quadratic. Well, the issue is they only gave us 2 points, but did they really only give us 2 points? Remember what we talked about earlier? We got that axis of symmetry that cuts through it. That axis of symmetry is always going to cut through your vertex. So if I know the vertex and a point over here, don't we also know a point right there? Yeah, that's 3 points now. You need 3 points to write the equation of a quadratic, and we now have it. So here's our graph. Let's write the equation. Let me scroll down a little bit. Y equals, let's do the vertex, minus 4 squared plus 5. That has a vertex of 4 comma 5. Let's check for the multiplier. Over 1, it goes up 1. Multiplier is 1. Okay, last one. Vertex, -7, -9. Let's see. -7, -9 down here. Okay, so let's write the equation. X plus 7 squared minus 9. That's -7, -9 for a vertex. And the point, -5, -1. Okay, this one's a little bit more challenging. Let's see. -5, -1. Axis of symmetry. It's a lot of dashed lines right there. Equal distance away, symmetric, right there. I now have 3 points. I can write the equation. So I could plot my points. I could draw the line. We've got our parabola. And let's look at the relationship here. We only know this coordinate right here, and technically -5, -1, this coordinate right here. So from -7 to -5, that's actually 2 spaces over. And remember, we're always working with the information we're given. So when you're actually given the entire graph, you could maybe just try to do the one spot over, but we're only given this data. We're only given these 2 data points. So I have to go with what I'm given. So 2 spots over goes, let's see, how far is that? -9 is where it was, and it goes to -1. So what's the gap or distance between -9 and -1? It's a gap of 8 units. All right, well, let's see what we have here. Over 2, it went up 8. All right, over 2, it went up 8. Well, what should it have been? Let me go back to where we were. Over 2 should only go 4. The squared relationship, 3, 9, 4, 16. So over 2, it went 4. It's supposed to go 4. Over 2, it actually went 8. So 2, 4, notice that this is a multiplier by 2. It's double. Put a 2 in front. That's all you got to do. Okay? That's it for writing equations using either the graph itself or a vertex and another point or piece of information. Remember, we need 3 points to get a unique quadratic function. And once again, this was from the worksheet that we went through in class as well. So just another form that you can check through the answers. And those of you who are virtual as well, this could be very helpful.